Okay. With that, let's get started this morning into Chapter 3. We're going to take 2 days. Again, in the early parts of the course here, a lot of our material is a brief, condensed review of material that you've learned in previous courses, a lot of it being general chemistry. And then we're going to sort of go in a little more depth or a little more real explanations of what these topics are. Chapter 3 is about simple bonding theories. Again, the word theory, I hope you're in the habit of using it correctly now as a chemistry student, is an explanation of some phenomenon, some occurrence, all right, based on all of the available data and observations that we have to date. But it's not like some end-all, be-all truth that we think will never, be changed, or that's etched in stone. That might be a different way to say it. Okay, we accept that our theories are only as good as the evidence that we're looking at to explain them to date. And bonding is yet another example. The atomic theory is the classic example of how theories evolve as new information emerges. But bonding is another great case and to consider. All right? And so we're going to revisit in this first part of this chapter the earlier attempts to describe bonding in chemistry, all right, which have not been completely set aside, but they have a purpose. They give us a quick idea of a shape of a molecule. That's what we'll focus on today, or an estimate of how a molecule might behave. All right, but the more detailed, more intricate and accurate understanding is going to be described in Chapter 5, which is known as molecular orbital theory. That is the prevailing most accurate way to describe bonding. Now, it's also the more complex and challenging way. So we want to recognize there's a time and a place for that degree of depth and accuracy, but then there's also other times when it's just as good to turn to these simpler models that might be available to us. Okay. The reason that the models have evolved is that because these early simple models, while they accurately described or predicted certain behaviors of molecules, as just the nature of chemistry evolved, and chemists looked deeper and deeper into behaviors of molecules in reactions and shapes and bond angles, realized there were some limitations to our first attempts to describe the bonding. Just like with the atom, our early ideas about atoms were accurate until we could start to see things like radiation and discover the different subatomic particles, and the gold foil experiment that revealed that the atom was empty space. So when those new observations came along, we had to rethink the model, all right, and thus the theory explaining atoms. Okay? So for the most part, we are looking at the same model of bonding that, like I said, you learned about in Chemistry 1, which has been a pretty good description of how molecules are built from the atoms. All right? And the prevailing way we do this is that we understand that covalent bonding is easily described. Okay, and let's put in parentheses just that the way to summarize that discussion that I just had, although with some irregularities. And it was these irregularities or these special cases that we'll look at that led us to realize, okay, this isn't the best way to describe the bonding. Well, covalent bonding is easily described using what you guys know to be Lewis dot structures. In the Lewis dot system, any two elements that wish to bond share electrons, we say, and we call that pair of electrons the shared pair, right, of electrons. And technically, we usually acknowledge that one electron came from each of these atoms, but now each atom believes or feels that it owns that pair of electrons and has a full octet of electrons. So sort of the goal is that each atom attains a full octet, so 8 of electrons, right? Okay. Each atom, quote, owns any shared electrons between the atoms. Okay. That's how we can get X and Y to each have 8 electrons, even though we only have 14 electrons drawn in this system. We don't have 16, right? We don't have an actual octet for each. They're each sharing this pair here, this centralized pair that we have here. Okay. Sometimes we need double or multiple bonds, double or triple bonds, multiple bonds in some cases, okay, to achieve the octet. So the way multiple bonds occur, a good example of something that exhibits multiple bonds is carbon dioxide. Carbon is going to have to share 2 of its electrons with each oxygen. Each oxygen, in turn, also shares 2 electrons. So the easier way, of course, to draw this is with these lines, where a line represents a shared pair. I've converted those shared pairs into lines down here. Okay? So this is the case of multiple bonds. Right? Sometimes we end up with options for where the multiple bonds belong or can go in a molecule, and that's a topic that should be very familiar to you guys, since most of you just had your year of organic chemistry last year, and that leads to the concept of what we call resonance, right? And so resonance is the occurrence of multiple bonds being able, or I guess I should say multiple bonds able to be drawn in different positions in a structure. Okay. The reality is that the true structure of a molecule is a hybrid, right? It is a mixture, a combination of all the possible resonance structures. So a simple case of resonance would be the carbonate ion, CO3. If you set out to draw the carbonate, you would need 3 bonds to your oxygens. Generally, we try to put ions in brackets when we draw their Lewis dot structures. It's just a heads up to people. Hey, the brackets tell you right away that there's the wrong number of electrons for just the atoms that you see present. All right. The 3 oxygens would bring in 6 electrons each, valence electrons, so that's 18, and the carbon would bring in 4. So this should have just 22. but the 2 minus charge means we have 2 extra, so we have 24. Right now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But the problem is that our carbon is not at a full octet. So one of the oxygens needs to form a double bond. But why did I randomly choose the one at the top? All right. It could have been the one at the bottom right that formed the double bond. Or it could have been the one at the bottom left that formed the double bond. So this is deceptive sometimes for students in that they think that, and one of the ways you get these other resonance structures is you physically draw, especially since you've learned about mechanisms, you draw your arrows moving around, but the bond isn't necessarily moving. It's not doing that. These are just 3 different ways to represent how the electrons could be arranged and organized in this molecule. All right. Okay. And the real structure is a hybrid of these. And the way we know that is from experimental evidence of the crystal structure of a molecule like this. All right. So if you put carbonate, it'll form a solid in a lot of cases. It's a salt, especially when you put an ion in there, a sodium or a calcium or something like that. And you can take X-rays of really tiny crystals of carbonate. And the X-rays will basically, they'll be bouncing off the atoms or getting through the gaps between the atoms. You can think of the bonds as the space between the atoms. And this will tell you how far apart the atoms are. We know how long a carbon-oxygen single bond is in many, many other molecules. And we know how long a carbon-oxygen bond is in other molecules. So if you know how long these are, you could be looking for the single bonds and looking for the double bond. But what you see is neither single nor double bonds. You see all the gaps are the same. They're all equal in length, and they're a little shorter than a single bond traditionally is for carbon and oxygen, and a little longer than a double bond is for carbon and oxygen. And so, it's not like we see in different parts of the structure. We don't see, oh, there's the double bond on this one. There's the double bond on this. You can never find the particular double bond. You're seeing all the equivalent, bond lengths. So X-ray crystallography shows that the bonds in carbonate are all identical. In other words, we can't find 2 single and 1 double bond, like the structure shows. So this is proof, right, that the real structure is some sort of hybrid of the 3 resonance structures. And so there are a few different ways to attempt to draw that real structure. One of them is to use a dashed half bond, essentially, between the carbon and each of the oxygens. Okay, and in benzene, another classic case of resonance, you hopefully learned, right, you could put the little circle in the middle, which describes the alternating double bonds and the fact that they could be in any one positions, but it's really an equivalent, set of bonds all around. All the bonds in benzene identical to one another. Okay? Now, in the carbonate, all three structures, all three resonance possibilities are equal to one another. Okay, they all have, coming back to these, they all have a carbon double bonded to an oxygen in one case. They're all equal, and then the two carbon-oxygen single bonds. But that's not always true. And in some cases, one structure can be drawn that is a better arrangement than the others. And we use, does anybody remember what we use to identify which is the best resonance structure? What concept do we use to help us identify the best resonance structure in a group? Ben? It's formal charge, right? There's things like formal charge. There's things like oxidation numbers. There's a few different things that seem to be numbers that we account for in chemistry. But formal charges, yeah, are the thing that we use to identify the best resonance structure. Okay? So formal charges are, remember, the apparent charge on an atom, okay, in a Lewis structure. Could be in any. It doesn't have to be groups of resonance structures. So it's on any Lewis structure. So the apparent charge on a given atom in a Lewis structure based on the electron distribution. The formal charge on a given atom is found by taking the number of valence electrons on the unbonded atom minus the number of bonds to the atom in the structure that you're looking at minus the number of unshared electrons on the atom. Again, in the structure. Okay? So you start with the free atom. That's the way our book describes it here. You start with the atom free by itself, and then you're considering on the right, these two things are both after the atom has bonded. Okay? What's the formal charge? The best structures, okay, the best structures have minimal formal charges. So if you could draw one structure that has all the formal charges as zeros, and a second structure has charges of 0 and +2 and -2, that second structure is not as good as the first structure. You want minimized formal charges. Okay? They also have negative formal charges, Fc, on the more electronegative atoms of the molecule. Okay, electronegativity, a property that we'll actually come to again later in this chapter, in class today, maybe even, is a property that describes how strongly an atom pulls electrons towards itself. And so the atoms that are better at doing that are the ones that deserve, or should rightly have, negative formal charges, because they're more likely to be greedy for electrons and take on a negative charge as a result of that. Okay? And then the final criteria is that they have opposite formal charges close together. All right. This is really a physics thing here, that opposite charges the further they are separated from one another, the higher the energy is. Electron diagrams, Lewis dot structures, sorry. It's all about getting the lowest possible energy state for a molecule. And so if you have to spread out these charges, you're raising the energy of that molecule. All right? And so it's less likely to happen. Okay? Another thing you want to remember about formal charges is that the sum of the formal charges on all the atoms, so if you sum across all the atoms of a molecule, the formal charges equals the charge on the structure, on the molecule or ion. So in the case of carbonate, the formal charges would add to -2. But in the case of carbon dioxide, because it's a neutral molecule, the formal charges would add to 0. There is no charge on carbon dioxide. All right? So. Any questions on this? We'll do an example, but on the concept or anything, what I've written before we get to a specific example? Okay. I'll just pick a couple of these out of the book here. The thiocyanate ions. This is example 3.1, the thiocyanate ion, SCN with a 1- charge, has 3 resonance structures. Let's draw them and determine the best structure. So typically, not a guarantee, but typically formulas like this, SCN, are given in the order that the atoms are connected, the order of connectivity. All right? And that's a good thing to know because you need in your drawing of your resonance structures to maintain the exact same sequence. If you try to get a different resonance structure by swapping the sulfur and the carbon, for example, that's no longer a resonance structure. That is what? If you change the location of the carbon and the sulfur here, what you made is now what in relation to these other things over here? Isomer. An isomer. That's right. Just want to remember your terminology. Isomers, same formulas, same things, put together differently. Resonance structures put together the same way. The glue is different. The electrons are arranged differently. The electrons you could think of as the glue, right, in a molecule. And so you're using a different gluing method to put the same stuff together. All right? So SCN minus, we want to add up our electrons. We got 6 from carbon, or sorry, 6 from sulfur, 4 from carbon, 5 from nitrogen, and 1 from the extra charge. So that's 16 total electrons. You classically can start your Lewis dot structures for a group of resonance structures like I've done here with a single bond connectivity. And then you want to work from the outside in. You want to put all your electrons that you have left on the outside. And then if you run out, that's when you're going to start dumping double or triple bonds into the middle. Right? I think it's the way that I do it. There's other ways, but I think it's a pretty efficient way to do it. So we're going to make sulfur come up to an octet. All right? So we've used 2, 4, 6, 8, 10, 12, 14, 16. Nitrogen's come up to an octet. Carbon is not. So now we want to start to think about how can we get carbon to an octet. So we could take away 2 of those and make a triple bond to the sulfur. Or we could have, from the original, we could have taken away 2 from the nitrogen and made a triple bond to the nitrogen and kept sulfur with a single bond. Or each of the exterior atoms could have made a double bond to it. Right? So carbon needed 2 more bonds from the parent structure that I drew. And then how did it get those two bonds? This is a classic arrangement. Two from one side, two from the other, or one from each side. Okay. Each of these is an ion, so technically we need our 1 minus charge in there. Okay. And then we usually put in these little arrows. This is one of the deceptive things because that makes us think this is moving back and forth between these, all right? But it's not. The real structure is some combination of these three. And again, there would be experimental evidence to prove that. You know, this structure would propose that you could find a carbon-nitrogen single bond and a carbon-sulfur triple bond. All right? Whereas this one would propose that you find a carbon-sulfur single, carbon-nitrogen triple in length, right? And those are all different lengths, and then the two doubles. Right? So the formal charges will help us figure this out. All right. So the formal charge on sulfur, sulfur normally has 6 valence electrons, minus 3 bonds to it, minus 2 unshared electrons to it. So the sulfur has a +1 formal charge. Carbon normally has 4 valence electrons. It has 4 bonds and no unshared electrons, so it is 0. Nitrogen normally has 5 valence electrons, minus 1 bond and 6 unshared electrons, so that's a -2. By the way, if you add those up, just to confirm, they add to a -1. Right? That's the charge of the structure here. A little check that you can use to make sure you at least got some decent set of charges. Okay. Now we can't look at one set of charges and answer our question. We have to look at all our sets of formal charges. So we have to repeat this exercise. Sulfur in our second structure is 6 minus 1 minus 6, so it is a -1. Carbon is still 4 minus 0, so it's 0. And nitrogen is 5 minus 3 minus 2, so it's 0. Okay. And then the last case we have sulfur, 6 minus 2 bonds and 4 electrons, so it's 0. Carbon is 4 minus 0, so it's 0. Nitrogen is 5 minus 2 bonds minus 4 electrons, so it has a -1 charge on it. Okay. So now we have our 3 sets of charges, and we want to compare them to our rules for what the best structures have. So the best structures have minimal charges. On that basis, it's going to kind of rule this one out, right? This is the largest set of charges because of the 2 and the -1. These other 2 sets are 0, 0, -1 in different places, but these are smaller in the grand scheme of things charges. So either of these is better than this. Now, the next comparison, they have the negative charge on the more electronegative elements. Nitrogen is the more electronegative element in this structure. All right? Our trend for electronegativity is that it increases as we move right across the periodic table, and then decreases as we move down. So nitrogen is above sulfur, and so that trend's going to win out. Nitrogen's about the 3rd most electronegative element in the periodic table. Okay? So this is the most electronegative element. So this is probably the most significant contributor. But given that this set over here is the same numbers, it's not going to be quite an equal contributor, but it's not totally ignored. This one over here is really not going to contribute much to the grand scheme of things. All right? So when I talk about contributing, I'm kind of talking about like DNA, like molecular DNA, all right, of like parental genes, all right? If you look at my kids, and some of you have seen my kids, you see them, you say, oh, Dr. C, your son looks so much like you, right? But he came from me and my wife, but a greater maybe contribution of my genetic traits has been passed on to him than my wife's genetic traits, right? So all of these are going to be the, quote, parents, all right? So a molecule can have more than two parents. But this parent is going to be giving the most traits to the true structure, all right? And then there are some traits of my son that look like my wife, right? So but they're just not, they're a little harder to find. So there are going to be some characteristics from this. The evidence that we have to support that, again, comes from crystal structures, all right, of molecules, or from what we know about when these molecule reacts and bonds. When this molecule bonds to hydrogen, which is a +1, it bonds on the nitrogen end. Okay? The evidence is that the hydrogen is connected to the nitrogen, all right, because the nitrogen is the -1 charge. If this was the dominant structure, right, let's logically work that out. If this was the dominant structure, sulfur is the negative, the hydrogen would come in on this side over here. But that's not what we observed. So that's a piece of experimental evidence. How hydrogen interacts, how a positive thing interacts with a molecule, shows you experimental proof of where the negative part of the molecule is. Okay? Yeah?
Is there a way you would write that with like the dotted half bonds like before that demonstrates that the dominant structure, or is that something you just write them all out and say, hey, this is...
Yeah, I think for a case like this, we write them all out. And what we see in the crystal structure is bonds that are fairly close to double bonds, as it turns out. All right. We do see that this one, this is all in the book, by the way. This is all fleshed out in the example. That's where I'm quoting all these things, is that where the hydrogen attaches, and that this bond is a little bit shorter than the traditional carbon-nitrogen double bond. That's because this structure, we've got to sort of blend triple bond, double bond. And this bond is a little bit longer than a carbon-sulfur double bond because, again, we're going to blend the fact that there's some contribution of that carbon-sulfur single bond when we look at the crystal structures of it. Okay? So resonance structures are, in the grand scheme of things, we also want to remember that the whole existence of resonance structures is a big flaw in the concept of using Lewis dot structures to describe the bonding in molecules. But it is, as this chapter is titled, it's a quick and easy way to get an understanding of how a molecule is put together. And it's much quicker than, as you'll see, the molecular orbital theory that we'll get to later on in chapter 5. Okay? All right. Any other questions? There's two more good examples of these resonance structures on page 48 in your text, all right, with some of the experimental evidence, the discussion that talks about sort of understanding, putting into context, why a particular structure might be the best resonance structure. Okay? Now, the idea of resonance structures also leads us to the concept of octet exceptions that you learn about in General Chemistry 1. Okay? So many cases occur in which the central atom of a molecule will not attain an octet of electrons. Okay. But has a preferable formal charge. And what I mean by that, preferable, so you're talking about a comparison. So I'll put in parentheses here, compared to if it did have an octet. So a couple of cases where this occurs, boron and beryllium. these are allowed to have less than 8 electrons. In particular, beryllium is often content with 4 and boron with 6 valence electrons to give them a 0 formal charge in structures. Okay? Many other atoms are allowed to exceed the octet rule, exceed 8. To do so, the key to being able to understand when an atom can do that, to do so, an atom must be in the 3rd period or lower. So what's happening in the 3rd period is that there are d orbitals available. Okay? Once we're looking at the 3rd period of the periodic table, we're in the 3rd energy level. That's the first case where d exists as a sublevel, an orbital type. And in the p block of the periodic table, elements like sulfur, phosphorus, chlorine, okay, those elements, their first set of Ds are empty, sitting there, but they could be places where electrons could be housed for resonance, for Lewis dot structures. Sorry. Okay, so these are some of the possibilities. As an example, consider SNF3. We can draw a structure for SNF3. The sulfur is going to be in the middle of this structure. We would have 6 plus 5, so it's 11 plus 21. So we'd have 32 electrons on this. So that is perfect, like this. So everything seems content. You got 8 on all your outside atoms. You got 4 bonds to your central atom. You've used all 32 electrons. Everything looks good. But from a formal charge perspective, the formal charge on sulfur is 6 minus 4 minus 0 plus 2. The formal charge on each of the fluorines is okay. 7 minus 1 minus 6, so there's 0. And the formal charge on nitrogen is 5 minus 1 bond minus 6, so it's minus 2. This is bad. In particular, this is a bad set because the most electronegative element in the periodic table is fluorine. And in this way of describing the bonding, you've given preference for nitrogen to draw more electrons to itself, essentially. To take even though the bonding is all equal, what these charges are telling us is that nitrogen has done something that makes it more negative than fluorine. And that's just not going to happen. Okay? So how can we get around this? Well, nitrogen having too much, right? Understand what these charges mean, right? Nitrogen has too much electrons density. It's weird to say too much electrons, but I mean, that's really what it means. It's too much electron density. And sulfur has too little. But they're connected. I have too much, you have too little. Here, let me shift some over to you, right? Let me take some of my electrons up here and push them down towards you. I still have 8 valence electrons, but if I form a triple bond as nitrogen and keep the fluorines all the same, now my sulfur is 6 minus 6 minus 0. It's come down to a 0 formal charge. Fluorines are still 7 minus 1 minus 6, 0. And nitrogen is now 5 minus 3 minus 2, It's 0. We've been able to get all zeros as the formal charges. Okay? The only funny thing that's going on now is that sulfur has 12 valence electrons on it. Okay? But, you know, that's actually not a problem. Sulfur's big enough, it's got space, it's got these empty orbitals accessible that could be holding those electrons, all right? See, sometimes we get too hung up because of how we learn about stuff back in general chemistry, and actually in organic, everything pretty much follows the rule of 8 electrons, okay? But that's not actually a hard and fast rule, right? The real thing is formal charge. Structures are set up to minimize the formal charge that you can achieve on all the atoms. Okay, so expanding these octets is perfectly allowable. Okay. All right. Any questions on octet violations? Yeah.
For boron and beryllium, I know you said one was 4 and 6, but I didn't catch them.
Boron would be 6, beryllium would be 4, just because beryllium has 2 valence electrons, and so it's going to form 2 bonds to bring it up to 4. Boron has 3 valence electrons, so that would bring it up to 6 total when it forms 3 single bonds, ideally. If you make boron go to 8 electrons, it would have 4 bonds to it, and then its formal charge would be 3 minus 4 bonds, so it'd have a -1 formal charge. It's on the left side of the periodic table, so it is not electronegative at all, so it does not want to have that negative charge on it. Okay? So we say, whoa, just stick to having 3 bonds. Okay? All right. So after all the bonding stuff is settled, one of the major properties that bonding theories attempt to predict is the shape and then thus the molecular polarity of a molecule. And that shape is predicted, I hope you recall, by the VSEPR theory. VSEPR, meaning the valence shell electron pair repulsion theory. The idea is that these shared pairs of electrons around the central atom of a molecule, they physically need space. Right? They're actual things, electrons, and they need space, and they need to be away from the other pairs of electrons. So there's a love-hate relationship going on here. Each of the pairs, or multiple bonds in some cases, needs to be close enough to the central atom that it's still, part of the central atom, and it's holding these atoms together in a bond, but it also needs to be away from other bonding pairs that are trying to do that same thing. Okay, that's the love-hate part. I want to be in close, but I want to be far away from the other things, so that would, there's a push-pull going on here. So depending on how many pairs you have in play around a central atom, they're going to set themselves up in very different arrangements. And we learned the classic cases of these back in Chemistry 1. I brought a little handout today that summarizes all these shapes. We can add a couple to it. Maybe there's a little bit of room on the back here. Let me pass this VSEPR summary out. So this sheet summarizes for you. You want to look at the front side, the VSEPR theory side. Okay. A generic way to think of any molecule would be A, X, M, E, N. So A is going to be the central atom. X are going to be the exterior atoms. exterior. And E would be any unshared electron pairs on a structure. M plus N, so the sum of the subscripts there, is equal to what we call the steric number. Not every textbook defines it this way, but our book is using this term steric number. Okay? Steric number, in general chemistry, I think of it as just the total number of groups of electrons on the central atom. That number is what is in the first column of your handout, just groups of electrons. So if you want to make this kind of match up with the way our book is doing it, this first column would be the steric number. Okay. So those groups can be all entirely shared, in which case there would be no E. You would just have an AXM molecule. All right? Or if they are unshared pairs of electrons, that's when you would have the E's. Now the E's are not part of the formula, right? So you have to recognize that. Like CH4, that's an example of AXM. But H2O, this is actually an AX2E2. Because when you look at your H2O Lewis dot structure, okay, these are your two unshared pairs of electrons. So it's not the formula per se that tells you which category you fit into. It's the Lewis dot structure. All right? So I don't want you to jump to a conclusion too quickly based simply on the formula here. You must first write out your Lewis dot structure and then merge it into this case over here. All right? So all things being equal, then, if we quickly refresh our memory here, if all the pairs are shared, if you have two groups, all of them shared, it's linear. Three groups, all of them shared, it's trigonal planar. I'm going to skip to four groups, all shared. We call that the tetrahedral case, right? You're most familiar with those geometries, probably from organic. And then if we go down to five groups, that's called a trigonal bipyramidal. Six groups all shared, you're in the octahedral family of the compounds. Okay? Our book goes a little further and acknowledges that you can actually go up to 7 and 8 total groups on the outside of a molecule. So on page 52 of our textbook, you see some additional Vesper shapes that you probably have not seen before, for having 7 or 8 outside groups. The 7 family is called Pentagonal Bi-Pyramidal, really similar to the trigonal bipyramidal, but instead of having a triangle around the central atom in the plane around it, you have a pentagon. All right, so 5 groups. If all of them are shared, you have a linear sort of axis like that, and then you have your other x's in a plane, right? And we use our wedge and dash system to represent our 3 dimensions. But for 7 groups, it is similar to this. We still have A in the middle, and then an axis of x's, and now we're going to have a pentagon of x's around it. Okay? So this would be a 5. These aren't bonds. I'm just kind of drawing in to show that that would be a pentagon or a plane around the outside. So the name of this is Pentagonal Bi-Pyramidal. Okay? And if we went up to 8 groups around it, we call it square antiprismatic. Okay? square antiprismatic. So I'll start with the name. So we're going to have two squares of 4 x's, one above and one below. But they're not going to line up vertices to vertices. They're not going to line up directly on top of each other. One is going to be rotated 45 degrees relative to the other. Okay? So one would have wedges coming up and out and then back like that. So you see there's a square up top, and then the other would have a wedge coming straight out. How would I draw that? A wedge going straight back, and then these are in the plane. Again, this is a square like that. So what you really have is one square on the bottom, and then one square on the top like that, so that those points don't line up with each other. The book's got sketches of it as well. All right, but in this case, in these two cases, these are the new violations of the octet rule. A has 14 valence electrons, and in the 8 groups, A now has up to 16. They're a little rarer, obviously, and they require the central atom to be pretty big, pretty significantly large, so that these bonds and these groups are spaced out from each other. You know, you need a bigger, you can't, just think about a little pin cushion or something, right? A little tiny pin cushion. You just literally can't get as many pins into a small one versus a bigger one that has more surface area, right? So a larger atom in the middle is going to be necessary to accommodate. These are kind of like the extra pins that you're trying to stick into that atom. Okay? All right? Very good. Any questions on that? Again, my drawing is not the best, so you can check out the images in the book. Now, so where we traditionally start is with everything being bonded. And then we start to figure out, well, what's the impact of lone pairs or of multiple bonds? And as you hopefully recall and can see on your summary sheet, lone pairs of electrons warp the shape of a molecule because they are held more tightly to the central atom than a shared pair. Okay, they're held more tightly to the central atom of the molecule than a shared pair would be. And so in the case of AX4, the classic tetrahedral, the interactions between all of the shared pairs, okay, are equal, all right? So these are what we call BP, bonding pair. Shared pairs or bonding pairs, but our book's using the term bonding pairs here. So in this case of AX4, all the BP interactions are the same. If we replace one of our shared pairs with a lone pair of electrons, so we move to AX3, we now have bonding pair interactions, and this is a lone pair bonding pair interaction. All right, that's occurring between the lone pair and all three. The lone pair bonding pair repulsion or interaction is sort of stronger than a bonding pair interaction. So you need to give it more consideration when thinking about the shape of the molecule. And the strongest of these possible interactions would be lone pair. So A with two lone pairs, two X's. Now you have lone pair, bonding pair interactions. You still have a bonding pair interaction, but you now have a lone pair interaction. Okay, these two are adjacent. The LP-LP interaction is the strongest. It's stronger than LP-BP, which is stronger than the BP-BP. So what that means is that the lone pairs want to be furthest apart. And we know this. We've studied some structures, like we know that the bond angle in water, the bond angle starting over here in methane is 109.5 for all of the bonds. They're all equal. But when we go to ammonia, where we have nitrogen to 3 hydrogens, now the bond angle shrinks up to like 107 degrees because the lone pair pushes on the bonding pairs, right? Pushes them away from itself, meaning they're pushed towards each other, the bonding pair interactions. And then if we go to water, where we have two lone pairs, they really push far apart from each other, which pushes the bonds that are actually left closest together down to about 104.5 in the case of a water molecule. All right? So if you're trying to think about the shape of a molecule, if you're trying to predict how it deviates from the parent geometry, you want to give the strongest consideration to the strongest interaction, the lone pair interacting with other lone pairs. This also helps us predict for more complicated geometries, where does the lone pair belong? If we come to this molecule here and we want to, for example, replace one of the X's with a lone pair of electrons, where does it belong? Should it go up here on the axis? Should it come out here on the equator? And the argument would favor it being on the equator in this case, because that lone pair gets to be 120 degrees away from two other bonding pairs. It's 90 degrees away from two bonding pairs and 120. If you put it up here, it's 90 degrees away from three bonding pairs. So you have three of that, stronger interaction that you don't want. You're trying to minimize that strong interaction. Okay? And so that's why that would go there. Here, now, that probably would, let's see, would that flip? What's the angle in a pentagon? 360 divided by 5 is still 100 and some degrees, all right? No, that's not right. It's 70. Oh, yeah, so these angles are only 74 degrees. So now it's probable that our lone pair would go on one of the axial positions, because it would get to minimize. Here you'd have two 74s and two 90s. Here you'd have 5 90s. Maybe it does belong on the equatorial position. All right, so we can think about these arguments that we'd have. All right, wouldn't really make a difference here. Everything starts out equivalent. All the positions would be the same no matter where you put it. Okay, at the start. But that's how we can use this idea of interactions of the bonding pairs versus the lone pairs. Now, multiple bonds have the same type of impact on a molecule. Earlier, I had drawn the two resonance structures of NSF3. one with a single bond and one with a triple bond, right? Again, there'd be some experimental evidence that that triple bond really exists because it does not have a true tetrahedral geometry. If we had all single bonds, we'd expect a nice even distribution of those 4 bonds. But in reality, we have a triple bond, or really close to it there, and that needs more space. Okay, it's taking up more space for itself, that increased amount of electron density, and so it's going to push the other 3 bonds down and away from itself. So multiple bonds have a very significant impact on the shape of molecules as well. Okay, all right. Let's see. All of this leads to what we'll be getting to sort of to next class is predicting the polarity of molecules and when molecules are polar or nonpolar. That's, again, one of the major reasons why we're concerned with the shape of a molecule. Of course, from organic, you might recall that you're often concerned about the shape so that you understand the mechanism, where a molecule is likely to be attacked. Okay? That in part depends on the shape. Which opening is literally big enough for sort of an attacking group to come in, or if there's what would you know as steric hindrance. Okay? So all those concepts are connected to the shape of a molecule, which comes from the simple bonding theories. Right? And so Vesper pairs pretty nicely with Lewis dot structures. However, the real flaw is, we've already identified the idea of resonance, but the other major flaw of Lewis dot theory and Vesper theories is they don't tell us a lot about the energetics of molecules and how energy is going to interact with a molecule. That's going to be part of molecular orbital theory that explains the bonding in a totally different way. It's really good for predicting the energetic stuff, not quite as good for the simpler stuff. Okay, so we're going to see a real difference in those two. Okay. Now, one other interesting little thing about shapes of molecules, which isn't really acknowledged when we first learn about it in Chemistry 1. So in Chemistry 1, we would say that it doesn't really matter what the exterior atoms are on a molecule, that the bond is going to be the shapes are going to be the same. So like in Chemistry 1, we would say like an NH3, right, has the trigonal bipyramidal shape, and it looks like that, and the bond angle is like 107.5. If we change the H's out for F's, boy, we should draw the exact same Lewis dot structure, really draw the same shape for the sketch as well. However, the bond angle here, well, we know to be 107 degrees. Over here, the bond angles are going to be less than 107 degrees, as it turns out. That's because fluorine is more electronegative than hydrogen. So in each of these nitrogen-fluorine bonds, the shared electrons are literally getting pulled out towards the fluorines. And if they're getting naturally pulled further away, the lone pair up here gets to take advantage. Not only do they move out away, then the lone pair can say, you can also push closer together, and you're still, this will be an argument we'll talk about on Tuesday of next week, the two pairs can still be the same far distance apart. All right, this is kind of tricky, but watch my hands right now. See how far apart my hands are? When they're held in closely, if you can imagine the angle from, let's say, my right hand to the knot of my tie to my left hand. Okay, imagine that angle. Now look at that angle as I move my arms out, keeping my hands the same distance apart. Okay, the two atoms have stayed the same distance apart. What's happened to the angle from my right hand to my knot to my left hand? Can you see it? Is it the same as the angle? the same? No. It's actually a narrower angle, right? So if we have this angle here versus this angle here, we can see that the smaller bond angle exists. Okay? And so the more electronegative element on the outside has this impact of changing the bond angles of molecules, right? Because it pulls the elements or the electrons away from the central atom. This totally flips if we put a more electronegative element on the middle. If we're comparing a series of molecules where the interior atom changes now, and we have a more electronegative atom on the middle, it's yanking the electrons towards itself, so now they're going to have to spread out as far as bond angles go. All right? Or if we go to a less electronegative element. Okay? So these are some subtleties that have been discovered that sort of layer on top of what we learned about VSEPR theory in Chem 1. And we also can look at molecules where it's not just an atom on the outside. What if this is a methyl group, a CH3 group, or a trifluoromethyl, CF3 group? Okay? We'll now get a really interesting argument. The book goes through this. CH3s versus CF3s. The CH3s are smaller, okay, than the CF3s. The CF3s are more electronegative. Which is going to win? All right. Well, in that case, the small size wins out. All right, and you get a smaller bond angle for CH3s than you do for the bulky CF3s. Okay, so it sort of justifies what you remember as steric hindrance from organic chemistry. Okay? This idea, all these are laying the foundation to get to a theory that helps us predict the bond angles in molecules that we'll look at next class period. All right? It's called the ligand close pack. We don't have enough time to get to it today. All right? The book also gives us a little bit, since I mentioned it, of explanation on electronegativities. All right? It identifies that we're using a slightly different set of electronegativity values than you may have used previously or than what you may see in your Gen Chem book. And so it's a warning, essentially. If you're asked to do any kind of a problem with an electronegativity value, please don't Google it. All right? What you're likely to find if you do a quick Google search are the values that are prominent in like a general chemistry book. And we're using a set of values that were developed, it says here, by the group of Mann, Meek, and Allen. They're on page 58 of your textbook. So there have been several different attempts to determine electronegativity values. Linus Pauling was the first person to do it, all right? But his system has been tweaked and improved to get a more accurate understanding of what this term electronegativity is. All right? Electronegativity, you should read this, it's really interesting. Pauling simply sought to understand why bonds were different. Why certain groups of atoms would form different polarities of bonds or different strengths of bonds. So hydrogen, HH, has one bond strength. ClCl has one bond strength. Okay? Why isn't the HCl bond equal, the average of those two? Okay? And he looked at tons of different bonds, and then that's how he developed this idea of, it's really an arbitrary system of electronegativity. Okay? And then others have then sort of built upon that. Okay? So you can't just randomly Google out electronegativity values. Okay? All right, your first homework assignment for Chapter 3 is posted to Moodle. Again, several problems from the end of the chapter exercises. Reminder, we will have a quiz at the start of next class on Chapter 2. Right? Otherwise, have a nice weekend, and I'll see you if you have any questions.